in Algebra 2. You have to do it in pre-calculus. It needs to be like a basic skill. Now, I have a lot of basketball kids in that class, not tons, but some, or just general athletes, like 9th and 10th graders, a bit immature. But I brought up the example. I was like, okay, have you ever had a coach, because we just did 4 examples, and we just did step by step by step. You have to do this first. Do it first to everything. You have to do this second. Do this second to everything. Okay. I showed them the box method, because after you guys, I was like, you know what? I think that's the easiest way for them to factor a hard trinomial, is the box method. Anyway, I was like, does a coach ever make you do the same thing over and over and over again in practice? No. No athletes? None? No. You never have to build skills?
Yeah.
Basketball kids, you never have to go shooting free throws? Like, you gotta be kidding me.
No,
I mean, coach just makes us
breakaway drills?
No. We run. Every day we run. It's the same thing.
Okay, well, there's a whole other reason for that. I'm talking about skill development. Why would you have to do drills? Why?
To get better at it.
To get better at what?
To develop muscle memory.
To some extent, because game day, you need it to be a habit, right? You can't be thinking about, like, well, how is my form for this free throw as you're shooting the free throw for, like, the game-winning point? Like, that's not going to work, right? It needs to be, now, some of it is you just get a lot of practice in, but some of it is you have to work on actual forms, like get your elbow in, get it underneath your hand, like anyway, bend your knees, right? If you're a basketball person. If not, I so apologize. There are other skills in other sports, and you should be thinking of them. Anyway, long story short, to some extent, there are certain fundamental skills in any class, in any sport, in anything, even like jobs, that you need to have down to be able to efficiently progress or efficiently do your job. Factoring is one of them. And you guys have already had to struggle through it this year, being like, oh, yeah, I didn't have it as mastered as I thought. Or, no, it was easy, so I just kind of sat here and twiddled my thumbs as everyone else had to relearn it. Factoring, we tried to develop and master. But what else do we need to develop and master? The unit circle. But just like factoring, do you know how some of you guys use the X method, some of you guys use the box method, some of you guys use grouping, some of you guys use guess and check? I guess that's just me. But anyway, there are different ways of getting to the end result. Do you guys know that one of the highest percentage free throw shooters of all time, he shot it underhanded? Yeah, he did a granny shot. He would go underhanded in the NBA. He had one of the highest percentage. He was in like the 95, 98 something. He had that percent for his free throw shooting, and he did it underhanded. Who would do that today in the NBA? Dude.
Me.
But back then, like, he was so dependable. And there were films made about him, documentaries, and all this stuff. Anyway, my basketball coach was a huge fan. He didn't want any of us to actually shoot that way, but that's okay, either way. There are different methods of getting there. Unit circle. Last year, Mr. Chay's class, did you have a blank circle you had to fill in?
Yeah.
Yes, but there are other ways. So let's get down the circle. Let's fill in the circle. Let's try to understand the circle. But then let me, for those of you whose brains just work a little differently, let me show you another way, because there is one. So, or 2, or 3. Anyway. P.S. No, I'll save that illustration for a second. I don't know why this year I'm just using my height a lot. It's not because something I deal with every day. So, there's a way my height will play into one of the shortcuts, just not yet. So, yesterday, we were counting by fractions, right? Okay. Pi, 3.1415926. In context of radians, rulers of radiuses measuring around a circle. Pi measures how much of a circle?
Half.
Think calzone, right? 1 pi, 1 calzone, 1/2 circle. Good. So, if I was down here in this quadrant, why does it make sense it's 7 pi over 6? Some of us didn't get to fill it in. It was right at the end of yesterday. Why is this 7 pi over 6?
Because you added pi over 6.
Pi could be cut into 6 pieces, 6 out of 6, and just add 1 more, right? So, why does it make sense that that one is 11 pi over 6? You had 2 calzones, both of them cut into 6. And you were 1 shy, how many 6ths would you have?
All of them.
No, all of them are 12. If you're 1 shy, if one's missing, somebody stole one before it got to the party, 11. That makes sense, right? It's fractions. Why does it make sense that this one is 7 pi over 4? Now my calzones, my 2 calzones, are cut into fourths. 8 total slices, 1's missing. Oh. Or 4 total slices, 1 extra. Oh, 5. It's just fractions. But what am I missing? There are like 1, 2, 3, 4 different angles that are missing fractions. This one is 1/6. If I have, check out the pieces, 1/6 plus 1/6, what should this one be? 2/6, yeah. But then 2 over 6 reduces to be 1/3. So 1/3, I have 2/6 making 1/3. You could just count by 6 and get there. But then you would have to start reducing, which is possible. So you could do 1/6, 2/6, got it. 3/6 is 1/2 pi. 4/6, well, if you want, you could also think in thirds. So 1/3 plus 1/3 is 2/3. 3/3, oh, yeah, the whole calzone. 4/3, oh, I have an extra piece. So what would this one be?
5 pi over 2.
Yeah, does that make, 5 pi over what? Yeah, 5/3, right? 6/3, where am I? Oh, duh, I'm back at 2 pi. It's just fractions. Now, yesterday we were filling in the root 2 over 2's, root 2 over 2's. It's a special geometry triangle, 1, 1, root 2. Whether or not you have it memorized, you know it was back in your geometry days somewhere, right? A 45, 45 triangle. Wasn't there also a 30, 60 triangle?
Oh, yeah.
And a 60, 30 triangle?
No.
Okay. If you were doing like conversions, you could ask yourself, what does pi over 6 go to by multiplying, remember, building bridges to get rid of what we don't want? You could think about how 1/6 of 180 is 30 degrees. That's one way of thinking about it. 1/6 of 180 is 30. That's one way. And that could lead you to the special geometry triangle of a 30, 60, 90. I'm going to zoom in on it in a second. And you could also think about pi over 3 as being 2 30s, or you could think about it as being 1/3 of 180, which is 60. Which would be the exact same triangle, just oriented a different direction. Either way, we need to remember what the 30, 60 triangles had as their special ratios. But before we talk about the 30, 60, 90, can we pause and think about the 45, 45? What did I do yesterday to change up the 1, 1, root 2? Why was there this division? Does anybody remember? If this is in a unit circle, what's the radius? What's the hypotenuse of any unit circle? Not root 2. If you were to plug this into your calculator, or if you were to try to fit the root 2 triangle, it actually would pop out and be too far. So we scaled it back, and to scale back anything in geometry, I think you talked about like scale drawings and things like that. You just have to divide every single side by something. And so I know that the hypotenuse has to be a 1, so I divide everything by the hypotenuse. And that's how I got, hey, you'll fit in the unit circle now. You have a radius or a hypotenuse of 1, and that's how I got my little, my x's and my y's. After doing a little bit of rationalization. I'm going to do the same thing with these guys. We're going to start with what geometry told us. Geometry told us, you guys remember 1, 2, root 3?
No.
No. It was a thing, once upon a time. Or x, 2x, and root 3x. A couple different ways of remembering it. The 30 is the smallest angle. He has the smallest one. 1 is the smallest out of those 3 numbers. 1, 2, and root 3. 2 is the biggest. The hypotenuse is always the biggest. And that's across from the biggest angle, 90. And root 3 is a little bit in between root 1 and root 4. 2 is equal to root 4. 1 is equal to root 1. Root 3 is a little bit in between. He's the in-between angle of 60. But if you guys realize why I divided everybody up here, I'm going to have to divide this one too. Because this one says, you're too big for my unit circle. Unit circles only have a radius of, so I need to scale you back. And if I scale you back, I have to scale everybody back. guys recognize 1/2 and root 3 over 2 as a couple important people in the unit circle? And what changes if the triangle flips? Well, basically nothing. Across from 60 is still the bigger of the two fractions. Across from 30 is still the smaller of the two fractions. And across from 90, well, it's always 1 in the circle. It's just an application of our special triangles from geometry. So where does that lead us? Okay, before I get to the circle, I need to know that you guys know how to order your numbers. If I have 0, 1, 1/2, root 3 over 2, and root 2 over 2. These are all my possible x and y values in the unit circle. My question is, can you put them in order from smallest to biggest? What's the smallest?
0.
Got him. What's the biggest?
No, root 3 over 2. Root 2 over 2.
Root 2 over 2. 1. Why? Oh. Oh, never mind.
Hold on. What is 2 as a square root? 2 is equal to the square root of. What's 2 squared? 4. So the square root of 4 is?
2.
Isn't square root of 4 bigger than square root of 3 and square root of 2 and square root of 1?
Oh, I guess.
So 2 over 2 or root 4 over 2 is bigger than any of those dudes. He's up here. Oh, then put him in order. Well, who's the next highest? Rad 3 over 2. Who's the next highest? Rad 2 over 2. And then rad 1. Technically. Rad 1 over 2. Huh.
Oh, it's 1, 2, 3. Oh.
0, 1, 2, 3, 3, 2, 1. Let's see. All over 2. Square root of 3 over 3. 1 square root of 3. What? There's a song? Yeah, we'll get there in a second.
Yeah.
Okay, so hold on. What do we got? Have we already plugged in all of our root 2 over 2s because they go with 45s? Yes. Have you guys written them in your unit circle? I'm not so sure, but probably not. Maybe we should get them written in. We have our 0, our pi over 2, our pi, our 3 pi over 2, and our 2 pi. They're easy because it's 1, 0, 0, 1, negative 1, 0, 0, negative 1. Those just go by ones. Our 45s, they're isosceles triangles. It's a 45 this way and a 45 that way. So I go root 2 over 2, root 2 over 2. Negative root 2 over 2 going left, like an x, that's negative. Positive root 2 over 2, negative root 2 over 2, negative root 2 over 2, positive root 2 over 2, negative root 2 over 2. 45s are kind of easy because they're isosceles. 45, 45, they're the same thing. And they're the very middle, check it. They're the very middle, check it. They're the very middle angle of each quadrant. So, pause. Emily, come here. You're good. Stand right here. Who's taller?
Emily.
He's right.
They're really messed up. Okay. Shorter, taller. True?
The-
Okay. Question. I want you to think about this triangle. If you were to go over and go up, what's longer, the x or the y? X is the taller one, the y is the shorter one, right? How about for this guy? Y is taller, x is shorter. True? Emily is 1/2. I'm root 3 over 2. Pause. Why? Don't we have a shorter? And don't we have a taller? Okay.
You cannot say
So
that.
ready?
I shall
Fill in. What's my x? Longer or shorter? Me or Emily? Me, root 3 over 2. What's my y? It's Emily. Right? Does that make sense? Go tall, then go short. X, then Y. Now go to this guy. Short, then tall. So, who's the little one? 1/2. Who's the bigger one? Oh, you guys got it. Go second quadrant. Now I'm going to the left. A little or a lot?
Just a little.
Just a little. Emily, negative 1/2. And then go up a lot. That's me. But I'm going up, so it's a positive. Ready, set, fill it in. Go. Go all the way around. All the pi over 6s and pi over 3s. You're going over a little, up a lot, or
Over Latin, up the middle.
Picked on. Who said it's bad to be short? Sometimes I really wish I was. I love that.
Being short sucks.
Yeah. When you're short, you can push, or when you're tall, you can push.
That's by the troublemakers that hang out in my room.
I hate being short.
It's a push and no locker.
Some of you guys remember there is a way to memorize the signs. All students take calculus.
Oh yeah.
Or chemistry. Or
It was chemistry. College.
All students take college.
You don't take
That's kind of pressure.
I actually obtained college.
But not all students take college.
I actually obtained college.
chemistry is, I think, pretty much required.
Yeah.
Yeah.
Calculus C class.
Yeah.
But calculus is cool.
I know, right? That's what I thought. Anyway,
Ooh.
because the X's and the Y's are all positive, only the, who's S and P and C? Okay, hold on, we have to get to SOHCAHTOA, we haven't really done that yet, but that's okay. We'll get there. Okay. Do you guys go left of me and then up in Emily?
Yeah.
Did you go left of me and down in Emily? Left and down are both negative, right? Left and Emily, down to me. Over to Emily, down to me. Well, hopefully anyone watching it knows you, or else, yeah. The only people that'll probably watch the video is people this year, or if I'm for some reason gone next year. Like if I'm absent and I have them watch the video from the year before.
Oh.
That was nice. Hey guys, isn't that the entire unit circle?
Yeah. My brain's broken.
So what's missing in my fourth quadrant? All of my fourth quadrant. Did you guys notice? Is it to the right? Should all the X's have been positive? Yes. But what's wrong? I'm going down. Shouldn't that have been negative? Shouldn't that have been negative? Shouldn't that have been negative? That's weird. I messed up on all three. That's so ironic. I think there was a ghost and he went through and erased them all.
I don't think that missionary would do that.
No?
I don't think her teaching.
Did I have them make the exact same mistake 3 different times between yesterday and today?
I hate that song so much.
Oh, let me go find it right now.
Okay.
I don't get it.
So what are we supposed to use this thing for? There are other ways of memorizing it, and I'm going to show that today, but we need to figure out what we're actually using this for. But right now, this is like for last year, for Algebra 2, this is like, hey, I could fill in the circle if you had it all down, right? You could fill in the circle, you get ace Mr. Shea's quiz, although did he make you do radians or degrees? Both.
Yeah, both.
Both.
I'm pretty sure.
From like Minnesota. Anyway. Said both. Anyway, so 30, 45, 60, 90, and then you say 90 plus 30, 90 plus 45, 90 plus 60, and then 90 plus 90 is 180. 180 plus 30, 180 plus 45, 180 plus 60, 180 plus 90. 270 plus 30, 270 plus 45, 270 plus 60, 360. Anyway, there are different ways of doing degrees as well. But what are they going to ask us to actually do?
Oh, I love trigonometry.
That was fun.
Sine, cosine, tangent, cosecant, secant, cotangent. Wait a minute, they have something to do with the x's and the y's?
No.
It's really functional.
Pause.
Our is 2 seconds.
Pause. You don't have to think about the unit circle with x's and y's. You can think about them as having baby triangles. Can't you? Just check it. Didn't we talk about yesterday how there's a triangle at every single point? We could draw a little baby triangle at every single point. The x is the adjacent, the y is the opposite, and in the unit circle, what is the hypotenuse always? So if we were to do SOHCAHTOA, true? Oh, that didn't work. If we were to do SOHCAHTOA, what does SO stand for? Equals. And what is that in context of? Oh, opposite is y, hypotenuse is 1. So what is sine? sine of an angle is y.
Yay!
In the unit circle, if it's a little baby triangle, sine will be the how far up. Sine will be the y. Over hypotenuse is just always over 1. Cosine, so ka, right? Well, in the unit circle, that's adjacent or x over 1. Well, that's just x. Tangent, toa, right? Equals opposite y over adjacent x. How far up over how far over. Okay, so if that's true, maybe this chart won't be so crazy or so weird. It's literally unit circle. Imagining little baby triangles in there and saying, okay, what do we get? We get this. Sine is y. You can put a t or you can put a theta. It doesn't really matter. It's a variable that's just representative of an angle. You can put theta if you want. We've been doing thetas a lot. But the sine of whatever, of the t or of the theta, is going to always be the y. The cosine is always the x. The tangent is the y over the x. Cosecant says, I'll flip sine. Secant says, I'll flip cosine. Cotangent says, I'll flip tangent. Well, denominators can't equal 0, right?
Oh, that's right.
So both cosecant and cotangent have the same denominators. So they're going to be undefined when their denominator is 0. Which is, oh wait a minute, we can actually talk about that. Y is equal to 0 at when the points are flat, because they're not up or down. That'd be at 0, pi, 2 pi, 3 pi, 4 pi. Anytime it's on the x-axis at 0 or pi or 2 pi or 3 pi, those two are not going to work out. They're just going to have to be undefined. And secant and tangent are undefined when x is equal to 0, and those are at the 90s and the 270s. That's when theta is equal to 0. Nope, sorry.
Bruh.
Half pi. Pi over 2. 3 pi over 2. Come on, computer. Catch up. There we go. So in the unit circle, when you have whatever angle hitting at a spot, forming, well, that's not very obvious. Is that a 45? Is that a 60? I did a bad job. Ha. What angle would that be in the unit circle? 60. And 60 is how much of a calzone?
3.
A third, right? That's pi over 3. And he would be over an Emily up a me, right? So 1/2 and root 3 over 2. Who's who? Sine of pi over 3 is the y, is the up. And the up, opposite, right, is the root 3 over 2. Cosine is the adjacent, right? Which would be the Emily, 1/2. Tangent, okay, he's a little bit harder. Unless you realize it's the y over the x, the me over the Emily, it's the root 3. Oh, that's disgusting. It's a complex fraction. But wait, aren't all the fractions over 2? Can't I reduce that and say, oh, hey, it's just square root of 3 over 1. And then we could go through and do cosecant by flipping sine, secant by flipping cosine, and cotangent by flipping tangent.
Can't you ask me just part reference?
So we have to do the geometry.
Oh, you can. So, what's happening if I was to write all 3 of these, aka the 45 and the 30, and write all their points? Question, starting even at 0, what's happening to my x's, as in my x coordinates, as I come up the unit circle? What happens to my x's? My x's? I'm going over a lot, and then less, and then less, and then less.
You did that.
Right?
Good job.
Root 2 over 2. 1/2, and then getting to 0. Look at my x's. Aren't my x's going down? So my x's are going down. My sines are going down. My sin's going down. I don't know. Something silly to remember. Anyway, what's happening to my... Oh, wait. No. Who's cosine?
Me.
What is x? Oh, my cosines are going down. Bummer, wrong one. My sin's going up. I guess that's actually more the case of the world. But anyway, my cosines are going down as my sines are going up. You can think of a way to remember that. My cosines are going down as my sines are going up. My x's are going down as my sines are going up. I'm going over less and less and less and less as I'm going up more and more and more and more. That's the basis for my cheater chart. Okay. I'm going to go slow the first time, and you guys can be timing me after that. But the cheater chart talks about the first quadrant. Because if you can get the first quadrant, and if you know reflections, maybe you can go from first to second, from second to third, from third to fourth, just by knowing the first. What's in the first quadrant? Well, we have 0, we have 30, which is 1/6, a smaller fraction, 45, which is half of a half, or 1/4. We have 60, which is pi over 3, then we have pi over 2. We have to remember which angles are in the first quadrant. And the nice thing about the cheater chart is it tells us about sine and cosine and tangent. SOHCAHTOA, and then for the other ones, cosecant, and cotangent, we would take these and we would flip them off, right? So we have our angles, and we also have our trig. Now here's kind of a weird thing in the cheater chart. We technically put the y first and then the x, but just because tangent is y over x. So if we can fill in the y's, if we can fill in the x's, all we have to do is a fraction of this over this to be tangent. That's kind of like one way of thinking about it. And SOHCAHTOA, doesn't sine go first, then cosine, then tangent. It's just a way of remembering. SOHCAHTOA. You guys ready?
How many degrees is pi over 2? 90?
Yeah. So you would have your 0 degrees, 30, 45, 60, 90. Okay. The song is only for the middle parts, because the other parts kind of just naturally flow. Because we have 1, 2, 3. It's actually from Brazil. Luca. Never mind. I mean, it was Luca. Luca was the one that taught it, but most of you guys probably don't know Luca. But anyway, Luca taught it to me when he was in pre-com. There's a song for this. I'm like, okay, teach it to me. I think Salma knows it too, even though she's not from Brazil. I think Juan did anyway, her older brother. 1, 2, 3. 3, 2, 1. All over 2. And this is the awkward part because it's not technically the song. You just need to know what there are square roots as well. Square root of 3 over 3. 1 square root of 3.
That's not a song.
Yeah, it's a jingle. Leave me alone. 1, 2, 3. One of my friends, her uncles, came up with a Lego My Ego lyric. That's kind of cool. That's what
You came up with it?
Mm-hmm.
Lego my Grego.
Oh dear. Not the right one. 1, 2, 3, 3, 2, 1, all over 2. With square roots, kind of awkward, they're not there. Square root of 3 over 3, 1 square root of 3. Bum, bum. Wait, there are zeros and ones, but hold on. Sine is counting up. It would have counted up from the lowest, 0, to the highest, 1. Cosine's working the opposite way, so it's going from the highest 1 to the lowest 0. And then tangent, okay, technically, we could have actually gotten square root of 3 over 3 by dividing 1/2 over root 3 over 2. Wait, aha, it's wrong. No, it's not. Square root of 3 over 3 comes from the rationalization of 1 over root 3. These are the exact same thing. Bless you. Square root of 2 over square root of 2. That's how you get 1. Square root of 2 over 2 over square root of 2 over 2. They're the exact same. They reduce to become 1.
Literally.
This one, square root of 3 over 2 over 1/2. The over 2's reduce. And square root of 3, well, is square root of 3. So how do we get this one? Well, what is sine over cosine y over x? 0 over 1, 0. Ah, what's 1 over 0, though? Undefined. And if you want to be snazzy, you could be like, I know what undefined is. But you don't have to be that snazzy. It's the vertical asymptote of tangent. So you guys going to time me?
Algebra.
Do you have it written down?
Oh, I already got it.
I'll dual page it, but I won't look at that page, I promise. Why am I telling you this? There was a kid in high school a few years ago, actually a lot of years ago. Probably none of you came to see the play Les Mis when we did it back when LAB, if you did come. The one who was, who's the one that falls in love with, and then,
Ooh, my friend told me the entire plot.
I forget her name. I shouldn't.
Claudia.
Yeah, that one. The barkeeper's daughter. Who was like normal and the barkeepers were super crazy. But anyway, long story short. The girl who played that, she didn't do so hot in math in high school. She had barely made it through Algebra 2. She took a math placement test. She had to start back at geometry. Anyway, I was tutoring her in math. She had to get all the way through business calculus, and now she's like a financial advisor, and she's quite well for herself, actually. But she had to get through business calc, and she couldn't even pass Algebra 2. Do you know what she would write at the very top of every single assignment? Because she had to retake geometry and basically a college algebra, and she had to basically retake pre-calculus. She had never taken that. And Calc 1 and business calc. She would write the cheater chart. Every homework, every quiz, every test. And she would ace the trig every time. Some of you should just use the cheater chart. Ready?
Okay, ready?
Tell me when to go.
3, 2, 1, go.
Ah! Oh, I went the wrong way.
We'll restart.
Can we restart? It's the first time this year. Okay, now I'm ready.
2, 1, go.
That's not English.
1, 2, 3. How long did it take me?
Oops, like 21.
Oops. Does that really add a lot of time to your test taking, quiz taking, homework taking?
Yes.
No.
Yes.
How long would it take you to draw the entire circle?
Time is money.
Exactly. So use less of it and learn how to use the cheater chart.
So
Or
don't take that.
just have the entire circle in your head. So you're like, and think little and big. Think short and tall, and then the middle. That's what my brain does. So that's just me. So, what if you were to be given? Let's get rid of that. That just says the first quadrant. You can mimic it to the other quadrant. You guys hopefully already know that. What if they start giving you stuff like, no, seriously? Guys, it's still like 9 minutes out. What if they say find all 6 trig functions? First of all, what order are we going to do them in? So, toa, right? Sine, cosine, tangent. What would be the smart order to do next? Because we have to have all 6. All 6? I thought there were only 3. Wait.
Cosecant, secant, and cotangent.
Yeah, cosecant, cho,
Ryan show.
sha, cow. We have sine, cosine, tangent, cosecant, secant, cotangent. Why? Well, the cheater chart gives us those 3, and then these 3 say take these 3 and just flip, flip, flip. That's the strategic one. Which one looks hardest out of all of these to do?
D.
Okay.
Oh, no.
Not the first quadrant, right? Where is 5 pi over 4? Hold on! Fractions! Isn't that 1 and a 4th calzones? 1, boop, boop, and a 4th. Third quadrant. It's right there. So if you're a visual person, maybe you could land at the 45 right here in the 4th quadrant by thinking 4, 5 pi over 4 slices. And maybe you remember that an over 4, if you need to, 1/4 of 180 is a 45. Or maybe you'll just remember it's a 45, but maybe that'll lead you to something like, oh, isn't he the negative root 2 over 2? Negative root 2 over 2 guy? Or maybe you would just have drawn your 1, 2, 3, 3, 2, 1 all over 2 little square roots. That's not in the song, I'm sorry, it's just a thing. P.S. Square root of 1 is just 1, so it doesn't really matter. Square root of 3, 4, 3, square root of 3, 4, 4. Where does the 5 pi over 4 land? Isn't he in the pi over 4 column? Either way, we could end up with, for letter B, that sine is equal to negative root 2 over 2. Cosine is equal to negative root 2 over 2. sine over cosine, y over x is always tangent, or you can just write it from your table, but you have to know the signs. Cosecant. Ugh. Cosecant, would that be negative 2 over rad 2? Negative 2 over rad 2. Oh, hey, but when you divide for cotangent, because cotangent is cosecant over secant, or x over y. Here's the hard part, guys. With this one, they're not going to have that in the back of the book because they will have rationalized. Yeah. There's an easier way of seeing it, though. So both of these are negative rad 2. The other way of seeing it is that, remember how back when we did the geometry thing, this actually came from 1 over rad 2 rationalized? You could also just flip, but most people don't remember where this came from. They just memorize it, so it's like, okay, awkward, but I have to flip them. And get like the nice, neat, simplified version. But either steal your x for cosine, steal your y for sine, tangent is y over x, or just steal a row from your cheater chart. Oh, but wait, signs, positives and negatives. What did you guys tell me a second ago that ASTC stood for? How many trig functions are positive? All of them. All of them? All of them.
Everything.
How many ones are positive here? Anything based on sine alone. Sine alone? Who has sine alone? Well, he does, and he does. Cosecant is 1 over sine. He just has a sine. What's in this one? Anything based on tangent. Who's based on tangent? Tangent and cotangent, right? And then this one, anything based on cosine, which would be cosine and secant. Remember? These two are time. These two are time. And these two are time. Boop. Boop, boop. Are we okay? There are a couple more properties that are things. They're not like the main point of the section, but they are kind of helpful. Sine and cosine.
Oh no. I always do that.
Sine and cosine, they repeat every 2 pi. Like their cycle repeats every 2 pi. Positive, then positive. It's a cyclic. We'll learn about the graphs another day. But they repeat every 2 pi. Their range, they technically, sine and cosine can go on. I can keep spinning around my circle forever and ever without sine or cosine ever being undefined because they don't have denominators. But they will only go down to -1 and up to 1. Sine and cosine are very bounded because both of them are bounded by the adjacents and the opposites in the unit circle that can't be bigger than 1. So they're very bounded. And then we have these little even and odd properties. Because cosine is an x, if you go first quadrant or fourth quadrant, the x stays the same. The y changes from positive to negative. Sine changes from positive to negative. But cosine, he stays the same. So anything built on or based on the x alone is going to stay the same. But anything that has a y in it, which is everybody else, is going to flip signs back to the old-fashioned even and odd symmetry thing. It just might be helpful for a few homework problems, and it's helpful every now and then. So a couple things I'm really hoping that you get to take away from this section. We're not quite done, just giving you time to write. Is being able to visualize where an angle is in the unit circle if it's given to you in radians. Being able to visualize where an angle lands, which quadrant, and whether it lands at the 30, the down or up a little, rotation-wise, or the 45, in the middle, up or down, or at the 60, down a lot, up a lot, with the rotation, or on the x or y axis, positive or negative. where an angle lands based on fractions of calzones and what trig ratios go with them. Sine, cosine, tangent, cosecant, secant, cotangent. So, what if I was just to throw out just one sine of 9 pi over 4? Visualize first where 9 pi over 4 is. You can't have the cheater chart and be like, it's a root 2 over 2, but is it a positive or a negative? You won't know unless you know what quadrant. Ella, why positive? But I agree. First quadrant, but I thought that's only pi over 4. If you guys have 9 pi over 4 slices, don't you have 2 1/4 pies? Haven't you gone the full 2 pi and 1 more? Oh, you're back at the beginning. If you're back at the beginning, what sign would sine have in the first quadrant? Well, all they're positive. And then you could think about it as over and up the same amount, so it has to be that middle guy of root 2 over 2. Or maybe you're looking in your cheater chart at the pi over 4 column and realizing...
The minute left of class, you boomer.
Hey, you finished this test on 15. Root 2 over 2 is my final answer. Minute left of class. What? That's it?
Boomer.
So what? Oh, let's save that for like a homework question. Homework question. We need to grade 4.1 and 4.2 tomorrow. Are ready? We're about to ask you for cosine of 5 pi over 3. Let's get inside the unit circle. Where's that at?
Let's get down.
1/3, 2/3, 3/3, 4/3, 5/3.
Bruh.
Cosine, he's adjacent, right? If I was to draw my triangle? Is he over a lot or over a little to get to that 60 degree? Emily or me? Emily. 1/2. No, I don't know that. Okay, fine. In your cheater chart, wouldn't you have had square root of 3, 2?
And do you want the instructions?
Oh, cosine. Oh, 1, 2, 3. 1, 2. Oh, that's right. I just circled the wrong one. I could have gotten there that way as well. The instructions are ready. I can take them by the end of the day. Your folder is open. The skateboard is at your disposal. Corrections on top.
Regular.
Because I wasn't sneaking it in.
Miss D.
We'll get it.
Miss D.
Yeah.